Hi everyone, this is Chengguang Zhu from Microsoft Cognitive Services Research. Today I'm going to talk about our work on enhancing factual consistency of abstractive summarization. This is joint work with University of Notre Dame. Abstractive summarization has benefited a lot from the recent development of large-scale pre-trained models. However, despite the higher and higher metric scores, recent studies have shown that the generated summaries often contain inconsistent content with the article, which seriously affects the real application and deployment of such systems. Here we'll give an example. The article is about a tragedy event that kills the victim, Philip Braham, and his wife is Valerie. And on Israel's Memorial Day, there was a commemoration. And French Prime Minister announced something. Let's look at the summary given by the state-of-the-art system bottom up. While most of the words come from the article, which gives the summary a high Rouge score, if we look deeper, we find that it says Valerie was the victim, and on France's Memorial Day, Israel's Prime Minister announced something. All these three things are wrong. So, although this has a high Rouge score, we cannot deploy such system because of the inconsistent fact. To solve this problem, we propose three steps. First, we need to identify the facts in the article. Next, we need to represent the facts in a way that the machine learning system can understand. And finally, we need to integrate fact information into the summary generation process. To identify the facts, we note that as news articles often contain novel concepts and relations previously unseen in any existing knowledge graphs, no matter how large it is, so we choose to extract facts to form an open KG. In other words, we extract facts on the fly from the article. Specifically, we employ information extraction tool Stanford OpenIE to extract each fact as a tuple of subject, relation, and object. And all these three components are made of consecutive words in the article, like this example. And then we convert the tuples into nodes and edges to form a factual knowledge graph. Here we use the Levy transformation to also convert the relation into a separate node, so that we end up with an undirected knowledge graph with edges between subject and relation to object. Finally, we construct an independent graph per article, as the same name, for example, David in article A may be different from the David in article B. Next, to represent the facts, we use a two-layer graph attentional networks to get the knowledge graph embeddings. To start with, the initial node embedding, or the 0th layer embedding, comes from the last hidden state vector after applying LSTM on the words corresponding to the node. And now we can describe our model after getting the knowledge graph with facts. Our whole model is a fact-aware summarization model, or FASum. It is basically a transformer encoder-decoder for summary generation, and it is trained from scratch. The difference between FASum and a canonical transformer architecture is that in the decoder, each transformer block cross-attends to both the encoder outputs and the graph nodes. So for instance, in this example, there are 5 nodes, so the output of this cross-attention will be a bunch of linear combinations of these 5 graph nodes embeddings. So now we have a system that can generate summaries with better factuality. But how about existing systems? We don't want to throw away such systems. Instead, we want to improve their factuality. So the problem becomes rewriting the summary based on the article A and a system's output summary S. To do that, we propose the Factual Corrector model, FC. To train FC, we manually manipulated ground truth summary and let FC model to recover the original summary. So here the input is modified summary plus the article separated by sep, and then the output goal is the original summary. And then during inference, the input is the existing summary plus the article, and the output of the FC is the corrected summary. Let's now look at the experiments. We leverage CNN Daily Mail and FASum. The baselines include bottom-up, UniLM, and tconf S2S. To automatically evaluate the factuality score, we leverage the FACT-CC model, which is a BERT-based model that can output a score between 0 and 1, and higher score means higher factuality. Let's look at the result. As you can see, first, FASum compared with other baselines can always have a higher factuality score, while maintaining a comparable Rouge score. Secondly, the FC model, which is the fact corrector model, can improve the factual score with little change to Rouge. For example, it can increase the bottom-up's result on CNN Daily Mail by 1.4% in factual score with little change to the Rouge score. And very interestingly, it can also further improve the factuality score of the summary from FASum. Some people may argue that if a system copies more content from the original article or be more extractive, then the result will be more factual. So we verify whether our model just achieves higher factuality score by copying more words. It turns out that it's not. So here we measure the abstractiveness of a system by computing the percentage of novel n-grams in the generated summary. And a higher percentage means a higher abstractiveness. In other words, it copies less content from the article. As you can see, FASum, which is the red bar, has a very high abstractiveness score, close to the reference. So FASum does not simply improve factual consistency by more copying the article. Furthermore, we conduct human evaluation. On the left-hand side, we show that for FASum, the factual score is the highest among the baselines, while the informativeness is among the best. On the right-hand side, we do a side-by-side comparison between the bottom-up and the improved summary by FC, and also the UniLM and the improved summary by the FC. As you can see, most of the time, our factual corrector can improve the factuality of the generated summary from the given system. And here we give an example of the corrected summary by FC on the article and bottom-up summary we showed before. As you can see, FC keeps most of the tokens unchanged. However, it correctly puts the right entity into the right place. So the factuality problem for this summary is solved. In conclusion, in this talk, we introduced two models. FASum, which is a fact-aware summarization model that can improve the factuality of the generated summary based on a fact knowledge graph. And FC, a factual corrector, which can improve the factual consistency of any given summary from an existing summarization system. Thank you.